we already know what is the So in this session we are going to talk about the kinetic energy of the system of particles. So we will see how the expression of the kinetic energy of a system of particles look like. So here again I have taken a system like this. This is a coordinate system. This is the origin over here, and there are these three particles shown with the different colors. Actually my system consists of many particles, but I have not shown all the particles for convenience. Okay, so we already know what is the work done to take a single particle from position A to position B. Okay, from position A to position B, what is the work done to take a particle? Okay, it is given as WAB is equal to integral of F bar, that is the force, dot ds bar. Ds bar is the infinitesimal displacement, and the limits are from A to B, from initial position to final position. So this is in general the work done. But now here I am not talking about a single particle getting transferred from one position to another position. I am talking about the system of particles. Okay, now I am taking all these particles to the newer position. Okay, so then how my expression will work out? So we look here. Okay, suppose this blue color particle is taken. Let me select. So let me draw another blue particle. This was the color, I think. So here, this is the new position of this blue particle here as I shown. So this particle, blue particle, has moved from this initial position to the final position like this. Okay, so from initial position 1 to the final, let us call it different with a different name. From P to Q it has moved. Okay, like this, and then work done by me to take this from P to Q will be WPQ, from P to Q F dash bar dot ds bar. Okay, this is to distinguish from this force and this displacement, infinitesimal displacement. So here this will be the work done. Okay, now if I take this whole system all together to the new I will change this configuration. Okay, I will take this whole system of particles to the newer position. Okay, and not all the positions will be displaced by the same displacement vector. That means this PQ bar vector, okay, will not be equal to the displacement vector of this green color particle. For example, if I take this green color particle over here, then this vector, which is, let me show you with the black, yes, so this vector by which this green color particle is displaced will be different. Maybe it is ST bar vector. Okay, so this is altogether a new configuration. Okay, this whole system of particles, that is this red, green and blue color particles, I am not just simply translating it to somewhere. Okay, I am totally changing the configuration of the system. That means I am taking each and every particle to a new position. Okay, and this displacement which is occurring for each particle may be different. Okay, maybe equal or maybe different. So we are not assuming that it is equal. So now let's work out the kinetic energy formula. Okay, so now what will be the work done for ith particle? So I will erase this. Okay, so in the back of the mind, keep in back mind that I am taking this configuration from, not translating this configuration from one position to another position. Okay, the whole particles configuration, that is relative positions of the particles with respect to each other, are not same in the final configuration. Okay, so that will be the better way to talk about it. Now for the ith particle, what will be the work done? So work done will be force on ith particle dot ds I bar, that is displacement infinitesimal displacement of the ith particle, and this is from 1 to 2. Okay, so this is from 1 to 2. Now this 1 and 2 describes the configurations. Okay, they are not describing the initial and final position of this particular particle. They are describing that in the second configuration, whatever position it will take, I will write it as a final limit, and whatever position it takes in the initial configuration, I will write it as a initial limit. Okay, then what will be the work done? Total work done to take it from 1 to 2. Okay, so this is the for ith particle. So total work will be W12 summation over I 1 to 2, this is Fi bar dot dsi bar. Now here if you look that I am putting 1 and 2 limits over here. So this work is the sum of all the works which are required for each particle. So for each particle, whatever work is required, we are adding for summation over I. That means we are adding over all the particles this work. Okay, now in each particle you will say the limit is same, right? Because if I write this, expand it like this, suppose F1 bar dot ds1 bar 1 to 2 plus 1 to 2 f2 bar dot ds2 bar, you will say that the limits are same. That means the change in position is same. No, it is not actually that. Here you have to note down that this 1 and 2 limit is not indicating the position of this particle. Okay, rather than it is just saying that the position, this limit 1 which you have to put it, is the position of this second particle in the first configuration, and here the limit that you have to put is the position of the second particle in the second configuration. Similarly here, first particle in the first configuration is this position. Okay, and in second configuration this is the position. So don't consider it as a position because same positions. Okay, so this will be different for different particles. So now this is cleared. So I will write like this, but we already know that Fi bar is equal to Pi bar dot, because force on ith particle is nothing but the rate of change of that momentum of that ith particle. So this will be summation over I 1 to 2 Pi bar dot dotted with dsi bar. Now one thing that we have to constant, so I will write it like this, summation over I from 1 to 2 Pi bar dot, instead of Pi bar dot what I am writing, mi dvi bar by dt dot dsi bar. So instead of dsi bar I will write vi bar dt. Okay, so now this dt and this dt I can cancel out, so this will become integral over 1 to 2. Since dot products are commutative, I can write like this, mvi bar dot dvi bar. Okay, now this whole term is what? Okay, what is this whole term? Suppose I have this half mi vi square. Okay, and I vi is my variable over here, mi is my constant. If I take a differential of this with respect to some variable alpha, so it will be half mi, okay, 2 times vi, that is the differential of vi, into dvi by d alpha. Okay, so here what I am getting is mvi dvi, okay, and by d alpha. So this is equal to, I will make some space over here. So this d by d alpha of half mi vi square is equal to mi vi dvi by d alpha. So here this is nothing but d of half mi vi square must be equal to mi vi dvi. So same thing we are going to do over here. Instead of this mi vi bar dot d vi bar, I am going to write it as d of half mi vi square. So this is from 1 to 2, the integral, and this is summation over I. So in this way, if I take the integral over this, so if I have some dx and if I take the integral of it from position 1 to 2, I will get dx integral as x, and the limits will be kept as 2 and 1. So this will be 2 minus 1, which is 1. Okay, same way this, instead of half mi vi square, you consider it as a x. So here it will be half mi vi square, this like this, and summation over I. Okay, so this is the expression. So here I will write like this: the work done W12, so let me write it over here. Work done W12 is equal to summation over I, okay, mivi square, half mivi square, okay, in the second configuration, minus half mivi square in the first configuration. Okay, so this is nothing but T2, sorry, I will write it summation over I here also. So this is nothing but T2 minus T1. So the work done W12 is nothing but T2 minus T1. That is the kinetic energy of the initial configuration minus, sorry, the kinetic energy of the final configuration minus initial configuration, which is same as the result we got for a single particle. Now here, if you see the kinetic energy term here, T2, that is T in general, can be written as summation over I, half mi vi square. So this is the total kinetic energy. This is nothing but the sum of the individual kinetic energies of the particle.